Good day. I am JM Subido, ID 120, and I'll be teaching ENGMEC3 LQ3. So for our first question, when drilling a hole in a table leg, a handyman uses a hand-operated drill with a bit of diameter D is equal to 5 millimeters. The first question under this problem, if the resisting torque supplied by the table leg is equal to 0.4 Newton meters, what is the maximum shear stress in the drill bit? So let me highlight what is needed. Then the next question, if the allowable shear stress in the drill bit is 34 megapascals, what is the maximum resisting torque before the drill binds up? And lastly, if the shear modulus of elasticity is G is equal to 80 gigapascals, what is the rate of twist of the drill? So let's also take note of the units for letter C because that will be handy later. So focusing first on problem A or question 1, which is A, we are looking for the maximum shear stress. So the maximum shear stress is denoted as tau max. And the equation or the relationship between the shear stress to the torque applied is denoted by this equation. So tau is equal to the torque times the radius all over J. Let me change C to R. So torque times radius over J. And the maximum shear stress in the shaft occurs at the outer surface. So in this problem, we have to focus on the outermost part. So it's important to take note of our D because R is just D over 2. So let's try to simplify the equation first. So this is equal to T times D over 2 from what was given in the problem all over J. And J is the polar moment of inertia. So for a circular shaft, the polar moment of inertia is equal to uh, J is equal to pi over 32 D to the fourth. So this is for this is only for a polar moment of inertia if it is a solid circular shaft. So since this problem, we will only have to deal with a solid circular shaft, given that the drill bit is solid and circular, we will use that formula. So this is pi over 32 times D to the fourth. And what we can do here is simplify. So let's put the 32 into the numerator. Let's put the 2 into the denominator. This would be equal to 32 times the torque times D all over 2 pi D raised to fourth. Now we can simplify this and this. The denominator would be 1, the numerator would be 16. Then let's also simplify the D. So in the numerator, there would be no D value, and in the denominator, it would be D cubed. So this would result to 16t over pi D cubed. And now that we have our formula simplified, let's plug in our values. So for A, we are given that our resisting torque is 0.4 Newton meters. So let's make use of that. 16 times 0.4 Newton meters all over pi times D cubed. So for our D, it's 5 millimeters. But since our numerator is in Newton meters, let's convert the denominator into meters as well. So that's 5 mm times 1 meter per 1,000 millimeters. So this would yield a value, we forgot the cube, sorry. So Let me just fix the, yeah. So, using a calculator, the answer would be equal to, um, 16, 16,297,466.17 Newton per meter squared. So that's in pascals. But we can convert the answer into megapascals, although it's not required in the problem, but it's better to just place it there. And uh, this would be 16,297,466.17 pascals times 1 megapascal over 1 times 10 to the 6th Pascal. So this would just be 16.297, which is rounded off to 30. So the final answer would be, let me write it properly, 16.30 megapascals. So this is for the first item. Now, moving on to the second problem, we're looking for the allowable shear stress. Oh wait, we're looking for the maximum resisting torque, sorry. Maximum resisting torque. So this is T max instead of tau max. So again, let's place our equation and simplify it already to uh, tau is equal to 16t over d cubed, since there is no changes in the configuration of the problem, so it's still a circular shaft and it's still solid. Then let's look for the value of t. So we're looking for the value of t, since that's what we want to maximize. So this would be t is equal to tau times d cubed over 16. So we're given an allowable shear stress of 34 megapascals. So it's here in the problem. 34 megapascals times the diameter, which is 5. So 34 megapascals, let's multiply it first by 10 to the 6th to make it in pascals so that we can get the answer more accurately. Then let's also convert the 5 millimeters again to meters. So we divide it by 1,000 meters, by 1,000 millimeters. So cube again, then divide it by 16. So for I forgot the pi, so let's put the pi here. It should be in the numerator. Apologies for that. So this would be equal to pi times 34 times 10 to the 6 times 5 millimeters cube over 1,000 millimeters, since it's converted, all over 16. And the answer would be, in Newton meters, 0.834. And we can already mark that as our final answer, since it doesn't require us to convert it into any units. So there. Now, let's move on to our last question for this problem. If the shear modulus of elasticity is 80 gigapascals, so we need to know the rate of the twist of the drill bit. So rate of twist. And here it's stated that it's in degrees per meter. Why is it such? Because we don't know, or we still don't have an idea of what the length of the drill bit is. So let's assume that it's the answer would be per meter. So why does this have to come in handy? Because originally, the formula is the rate of twist is equal to TL over JG. However, since we don't know our L, and since originally, the value here is only degrees. Here is only degrees. So what we can do is just convert it to this is equal to T over JG. And the units here would be equal to degree per meter, considering that the value we get here is converted to degrees. So in this case, our answer has to be degrees per meter. Well, let's get to it. Our torque is, we'll use the one that is given in the first problem. So it's 0.4. 0.4 Newton meter divided by polar moment of inertia, which is pi over 32 times d to the fourth, which is 0.005 meters cube. No, sorry, to the fourth rather. Then we're gonna multiply the G of 80 gigapascals, convert it to Newton meters, that's 80 times 10 to the 9 Newton per meter squared. So now that we have that, it's just simple plug and play. We will get 0.4 over pi over 32 times 0.005 to the fourth times 80 times 10 to the 9. And the answer would be 0.08147. So this isn't in degrees yet. This is still in radians per meter. So this is because there's no degree unit here. So the angle would be unitless. Therefore, it's in radians. What we do is multiply it by 180 over pi. So times 180 over pi, our answer would be 4.67 degrees per meters. And it's important to note that since the direction here is going to the left, we also have to include it in our final answer. So let me just place it here instead. The angle of twist is 4.67 degrees per meter to the left. So those are the key equations for the problems involving torsion. Thank you so much for watching. You may also avail syntax tutorials by scanning the QR code flashed on your screens. Once again, this is Jose Manuel Uisubido from Syntax, paving your way to excellence.